Okay, good morning again, everyone. I'd like to welcome us back to the concluding webinar. We had part of stable isotopes in the Rio Bueno SubWMU. We had our first webinar on Monday, which featured Dr. Aurel Persoy, and we spoke about isotopes in precipitation. It was a very interesting presentation, and they gave us a little tease, if you want to say, of the matter that we're going to look at today, looking at the actual sources in the Rio Bueno SubWMU. As you may know, this SubWMU is karstic, it's sensitive, it's been topical in recent times due to the recently approved bauxite mining in a very important section of the WMU, which is right in the middle of the study area. So the impacts and results of this study are going to be very crucial for ongoing research, current research, and ongoing water management in the Rio Bueno SubWMU and the wider dry harbor hydrologic basin. Well, enough from me. Let's get right to the meat of the matter, and we'll now turn over to Dr. Aurel Persoy to talk about stable isotopes in the Rio Bueno SubWMU. Aurel, over to you.
Yes, thank you. Thank you very much, Geoffrey, for the nice introduction and for hosting this, and everybody for being here and hopefully listening. Hopefully to something interesting for you. For me, it was very interesting and very nice to look at the data. And good, I think I should start. But first, I would like to thank Geoffrey and his team for collecting the data. It was a huge amount of data that was collected, and it is. I mean, it should be, and it will be, hopefully, useful for managing the water in the area. I will go directly to my presentation, and then we can discuss afterwards. Questions or comments in the chat, or save them for directly asking me after the presentation. Let me have my coffee ready. It is ready. Okay. I will need, I cannot share my screen, so if Geoffrey, you could enable this
Yes,
screen sharing.
My apologies. You should be able to do it now.
Yes, here it is. I don't seem to be learning. Please excuse me for a second while again I export it as a PDF so that I can move my mouse around on the screen. Okay, so let's stop this and let's start the other one. Just a second. Here it is. Okay, let's do it again. Should be. Okay, I think it's on the screen, and I think it's full screen now. Let me minimize this. Okay, so so I hope it's visible, and I hope, yes, I can see my mouse moving on the screen. So today I will be presenting a brief discussion of the data that has been collected by the Water Resources Authority of Jamaica in the Rio Bueno catchment, or SubWMU, I think, management unit, water management unit, if I got it right. So just very quickly, I will have a few slides at the beginning on karst morphology, karst hydrology, just as a recap of my previous talk that we had, I think, last year. And then a few slides again on stable isotopes in precipitation, 2 or 3 of them, just to set the stage for the discussion of stable isotopes in surface and groundwaters. And then I will conclude with a few lines about what should be done next and how could this data be used to understand what is happening in terms of recharge of the karst aquifers in the study area. So here we go. Yesterday I was discussing about this point number 1, isotopes in precipitation. Today I will be focusing a bit on point number 2, what is happening on the surface and what inferences can we make about what I think is happening in the underground. And please have in mind that today's discussion is only based on a limited data set. So it is data that has been collected and analyzed between March and August 2021. And the samples that have been collected since September until January are analyzed as we speak. So the interpretation is very preliminary. And the second thing that I want to say, so apart from the stable isotope data that I will be discussing today, Geoffrey and his colleagues have also collected a huge amount of data on water chemistry. And I will not be discussing about this today. And this is because, whereas when it comes to isotopes in karst system, I am more confident on what I'm saying on a limited data set, I cannot say the same about chemistry data. So I would only speak of what I am confident of saying. And this is because this is not a scientific meeting where you can, let's say, discuss some preliminary data, and then if in a few months or a few years you get some more data, then you can say something more, and then you can completely change what you have said. In this case, the reason why we are doing this is for water management, and I don't want to say things that could be that can turn to be wrong in a few months, because it's more important, you know, to get it right from the beginning. So I will be discussing stable isotopes only, with the caveat that this is preliminary data. It might maybe change, not that much, and I'm not going to touch into chemistry. So let's begin. So here is a very brief recap of karst. You can see a so-called comprehensive karst system, an image of it. Basically, what I want to show here is that we are having this in any karst area. We have an input of the water that can be point input through reverse sinking into karst, and or like here or here. And then we have input, diffused input on the surface through current, through dolines, spolias, and so on. These waters are mixing in the underground. And then sometimes there is input of water from juvenile water. This is a bit debated. We mostly have, yeah, it could be. Not the case here in the Bueno area, in the Rio Bueno area. And then we have the outflow. The point that I want to make here is that compared to porous media, where it is fairly easy to discuss how much water is in there and how the water moves, in karst we have the huge problem of the heterogeneity of the underground. So the problem is that we can have the spaces available for water can vary, not only between different regions, but within the same region. So we can have a huge underground cavities in the orders of tens of hundreds of meters. And these are, and these can act as both conduits for water, for a quick throughput of the water, and also as reservoirs for the water. So because of this heterogeneity and because of this complex mixing between the different types of input waters, it is very difficult to estimate the amount of water that can be stored underground. And here is a bit of details about the types of input and the type of permeability that we can have. So we have first the so-called matrix permeability, which is pretty much similar to other porous media, because this is the pores that we have inside the limestone, or whatever limestone, or let's say marble or so. Basically, it is the primary porosity of the rock. Now, this is not as important in karst as in porous media, because more important is the so-called secondary permeability, which can be further divided into fracture permeability and conduit. And by fracture, we mean all the secondary joints and bedding planes along which the water is moving. And then we have the conduit, which are the large cave passages through the rock. And what is important about this, I'm showing this with a picture made by Christos. You can see here the conduit. This is a conduit. Yes, it's a cave passage through which the water is moving. And you can see here on the ceiling these sphelothems, these stalactites, which are indicating joints, fissures, which are the so-called fracture permeability. So water is moving through these fissures, it deposits limestone, and then the dripping water is added to this river. So the water that will flow out of this cave will be a combination of river water here and the drip water coming through these fissures in the ceiling in this case. And depending on the size of the river that is going underground and the frequency of the fissures, the relative ratio of the two types of input can vary hugely. It can change, it can vary also with the amount of rain outside and so on. We'll see it later on. The second important thing is the recharge pattern that we can have in a karst area, and I'm showing it here. So we have the fairly simple case of river going in, flowing through a conduit, river going out. So here we have a sink and here we have a spring. We can also have several sinks meeting together into one main conduit and flowing out, or we can have a diffuse recharge through a series of fissures like the one seeing here, and all these are concentrating into one main conduit and we can have the outflow. Or we can have the case where there is no specific outflow, there is not a single outflow, but several springs or several points of water emerging from the underground. And this is again important because the relative contribution of the different types of the inputs are changing with the characteristics of the limestone, with the climate characteristics and the distribution of precipitation, the type of weathers that we have outside and so on. We will see later. So the bottom line is that if we are in a karst area and we see a sink or we see a spring, that does not necessarily mean that, and they are connected, let's say, that doesn't necessarily mean that what gets in through a spring is exactly what is coming out through the spring. There is some contribution from other types of inputs, mostly diffuse input that is adding to the point input. Okay, I think, yeah, and here is the example from cockpit karst area in Jamaica. You can see here is just to show the evolution of the general evolution of surface in a cockpit karst area. So we have streams on the surface, so we have diffuse inflow, and then once we form rivers, those will act as point inputs, but these will not be single, but the entire surface will also add the secondary input, the diffuse input. And that it's one of the main controlling factors is the frequency of the fissures and the frequency of these diffuse points. And if we are speaking about cockpit karst area like here, you can see there is a huge area that potentially can contribute to delivering water to the underworld, to the karst below. Okay, so there is a series. So we have the processes that were active during precipitation, and then we have processes that are active on the surface, and they have on the surface of the limestone before water is sinking underground. And then we have processes inside the karst, and all these are contributing to the recharge patterns of the springs that are emerging from the karst area, like the ones that we see here around in the northern part and the southern part. So it is the combination of processes on the surface and in the underground that are influencing the amount of water available. And it is this is very important because when we are comparing karst with non-karst areas, basically for non-karst areas, we are speaking about the climatic patterns and the infiltration. And then once the water is in underground, it's a quite well understood, well constrained system. So we can easily understand how much water we'll have in there and how much water we can assess. Whereas in karst, because of this huge heterogeneity of the limestone and the various types of inputs, it is extremely difficult to predict how much water will be there and how much water is there. So it requires in-depth analysis of both the karst processes and the hydrological processes. And today I'm going to be talking about these hydrological processes for the area. So here it is when we are speaking. When we are analyzing these hydrological processes, when we want to look at the stable isotopes. So I'm concentrating on stable isotopes. We are looking at the oxygen and hydrogen isotopes of water. Here is upper chart, and also we can look at the carbon isotopes in the dissolved inorganic carbon. And this is a very important component of this of the study, because if we look at the oxygen hydrogen isotopes, we can link the processes in the underground with the processes at the surface and with the precipitation, and thus further to climate. Whereas when we are looking at carbon isotopes in dissolved inorganic carbon, we can make a very good link with the processes inside the karst, like dissolution of the limestone, precipitation of the limestone, and in combination with just the typical tracing studies like dye tracing or so, we can infer something about the rate of the processes. And then if you understand the rate of this process, the processes and the rate at which they are changing, they are happening, we can understand what is happening in terms of what is happening with the water that is getting underground. And today we'll be discussing about oxygen and hydrogen only, as this is the data that is available. So here is the amount of information that we have. In the areas, precipitation was sampled at 3 stations, 7 river stations, 5 sinks, 15 springs, and 16 wells. And this, you can see the interest for springs and wells as water sources. The study period was between March and August 2021, and there is a second batch of samples that is being analyzed as we speak. And I know that Geoffrey is continuing the collection since February and March and so on. So this is work in progress. Okay, so the data that is plotted here, all the data, again, maybe you remember from yesterday, black is precipitation, the red crosses are the tropical storm grace, which in terms of information, we were fortunate to have. And I'm only speaking that when I say fortunate, I don't want to say anything about the devastation that this caused. So it's only that it allows us to get some more information, and you will see how important this was for our study. So first I will start with precipitation. The black dots indicate the precipitation, the monthly values at the 3 stations between March and July. And the red dots here, here, and here are the data that from August. So this was collected after the passage of tropical storm Grace. So you can see that the precipitation between March and July was fairly consistent. So the variability was something like maybe 6 per mil. And the variability in August was more than double that. So this was one single storm. And the red crosses are showing the delta O, the values of tropical storm Grace. So you see that it started with values similar to the precipitation and it quickly decreased to very negative values. The result of these very depleted values were these values for August, which are completely different than the values for the previous months. Okay, I'm showing here the temporal evolution. I put this chart, the nearest station that I could find was in Manville. So this is the average, this is the precipitation. This is not for 21, this is the average value. I got it from climatedata.org. So this is precipitation, this is temperature. I put it here just for illustrative purposes. And here I'm showing the temporal evolution of delta O18 in precipitation at the 3 stations. I'm only showing delta O18 because delta 2H follows a similar pattern, so it's the same. And then it's easier to visualize the data. So what is visible is that between March and July 2021, there was fairly stable values with a slight decrease towards the end of summer. And you can see here the influence of tropical storm Grace. So the values dropped precipitously. So from an average value of about -5 per mil for the previous 5 months, these dropped to an average value of about -8, -9 per mil. I did not get into the details of the differences between these two stations, so maybe in a future step, but the bottom line is that you can clearly see the strong influence of tropical storm Grace on the stabilized composition of precipitation in the study area. And then if you move further to river values, the colors are the same. So these are precipitation, the blue greenish group of colors, and here in yellow orange colors I'm showing 3 rivers out of the 7 that were samples for which we have continuous time series. And again, you can see that between March and July the values were extremely stable. Basically the variability was something like 0.2, 0.3 per mil on a monthly basis, which indicates that these rivers are fed not only by precipitation but very likely also by water that is running off from the surface aquifers, and also possibly by water that is reaching the study area from more distant areas. And it was very, very stable. And then I only have data for 2 stations in August, and you can see that both Pier 3 Bottom River and also here is St. Anne's Great River responded to a different degree. So Pier 3 Bottom River clearly responded in terms of stabilized composition of the water to the passage of Tropical Storm Grace, and St. Anne's Great River to a lesser extent. There is no data from August 2021 for Cave River at Bogus, only for these 2 rivers. So you can see that depending on how much water is coming from how much water is sourced from the region that has been directly affected by Tropical Storm Grace and how much is coming from outside of it, we have a different response of the rivers, but generally you see this response of the rivers. Now, if we go to the sinks, which are basically like surface rivers, smaller ones sinking in the underground, you can see again here, so the 3, these are indicating the precipitation. And here you can see with colors the rivers that I shown previously, and the 2 lines here are showing the 2 sinks for which continuous time series were available, and you can see that they have a similar behavior, very stable values throughout the year between March and July, and the response in August 2021 when the water was influenced by the passage of Tropical Storm Grace. So the same type of response, because these are essentially surface waters. By sinks, it is at the sinks, the water, it was collected the water that was flowing on the surface just before entering the underground. And the response, being the same type of water as rivers, is similar. However, when we are looking at wells, we can see that there was absolutely no change. So these are samples collected from wells. It is 3 wells, Brownstown, Hopewell, and Cardiff. And you can see these extremely constant values throughout the year and absolutely no response to the strong change in the delta O18 of precipitation. So that means that these springs, the response time, the recharge time of these springs, of these wells is less than a month. So there is a relation between the surface and the wells. And also it could possibly indicate that the amount of water that is available in these aquifers that are tapped by these springs is large enough to offset the influence of Tropical Storm Grace. But it is also possible that the response is delayed. So it takes maybe 2 or 3 or 4 months for this water to infiltrate. And once the data that is available in October, September, October, November will be available, maybe it will show that there is a delayed response. We don't know. But it will be very important to have this data, because then we can check what is the connectivity between surface waters and well waters. And then we can get an idea of how quick is the transfer from surface to the underground, and how these aquifers that are tapped by wells are responding to changes at the surface. And this will be extremely important, because then it can be further investigated, the role of climate in recharge and so on. So I will be extremely curious how these wells will respond to changes at the surface. Now, here comes the interesting part. And this is because we are moving into the springs. And as you can see, contrary to wells, the springs are responding in a similar manner. So for 4 springs for which we have data in August 2021, they all show this response. And what is interesting, and I'm showing in this second, so here it is the springs and the precipitation. So you can see that the springs are responding in a similar manner. And this is, so these springs are discharging the karst aquifers. So that means that the input signal was transferred to the karst to the output in a very, very quick manner. Now, the transfer time between the sinks and the springs, I don't know it, but it should be, because we see the response in springs. That means that the water that is emerging through these springs is being recharged in a matter of a few days at most, because tropical storm Grace passed over the area, nearby the area between August 17 and 18, and these samples were collected on August 25, 27. So it's something like 10 days between the moment the samples were collected in the springs and the passage of Tropical Storm Grace. So that means that the water of the depleted waters of Tropical Storm Grace reached the underground and then emerged as springs in less than 10 days. And I'm changing now a bit the background. So this line shows the precipitation, just to get an idea. And the 2 blue lines show the values of the sinks. And the reddish colors, these 4 are showing the springs. What is important, and I hope I'm right, in this chart is that the response of the springs is larger than that of the sinks. So what you would expect is that you have water getting underground, and then if you have a strong signal, it will mix with water in the underground, and then it will emerge on a muted signal. So theoretically, you would expect that the water that is moving underground will be depleted in August by, let's say, by about 1 per mil or 2 per mil, and the springs will be less than that because they will mix with underground water. However, what we see here is that the response is stronger, is extremely strong. So you see these very depleted values in the springs. So that means I interpret this as an indicator of the fact that these springs, so the water in the karst aquifer, is not only recharged by input points through these sinks, but there is also very important recharge through diffuse flow to diffuse recharge. So the water on the surface was very, very quickly infiltrating in the underground through numerous diffuse distributed points and was recharging these springs. So very likely something like we have here with so maybe something like here we have recharge of the aquifers that are emerging through these springs, both through points, sinks and ponors and so on, but also a very large and component of diffuse inflow. And I don't have data on the volumes of the water, but seeing this very large response, at least for these springs here, I would say that the recharge through diffuse inflow, distributed recharge on the entire surface of the karst area exceeds that of that is happening through the ponors or through the sinks. And I think this is extremely important for understanding how the recharge is happening in these karsts and how much water can be available for future. And also very important, the potential pollution of the waters, because there is, if we have a very large component of diffuse inflow, and for instance, the surface is disturbed by mining or other human activities, then we can have a very, very strong negative impact on the quality of the water underground. But this should be further checked with chemistry and so on, but this is only based on stable isotopes. So yeah, so here is just a bit of what I think is happening. So we have this cockpit karst area. So apart from the inflow through sinks, this entire surface acts as a distributed sink, let's say. So like a huge sponge through which large amounts of water are getting underground. So we see here this chart with the point infiltration, and this entire area acting as an infiltration area. And for at least for some of the springs there, the recharge to this area, this distributed, this diffuse infiltration is larger in terms of volumes of water than the point infiltration. But this needs to be further checked with the data. But the problem is that whereas we can quantify how much water is going in through a point infiltration, it's extremely difficult to calculate the diffuse infiltration, because we don't know exactly if we have infiltration somewhere here. We don't know whether this is ending in here, feeding the spring, or some of it will find other ways going out. And I will come back to this in a few slides. And here is this nice photograph by by Geoffrey. And I put it here just to exemplify this surface, this distributed infiltration. You see here the road is flooded by water. So I expect that this water, some of it will infiltrate, and this entire area acts as a source of water feeding the karst, the aquifer below, and then getting out through a spring. And this is extremely important because I'm showing here the link with yesterday's presentation. We don't know exactly. So this is what we've seen through one storm, one tropical storm. And because in future, the area sits at the crossroads between becoming drier but more variable and drier and less variable, it is very important because this variability that we don't know, it means that we can have huge amounts of waters delivered in very short time. And it's very important when these are being delivered and what is happening with the water. Because here I'm showing two precipitation and temperature variability. So here you see this type of distribution of precipitation and temperature. Here is a different one. And here you see how the delta O18 is completely different between these two. So plus, minus, it's not very strict, but we have a somehow drier season or less wet season and the wet season. Here is something similar, but with a different amounts, but the distribution of the delta O18 is completely different between the two. So depending on how in future the climate will evolve in the area, we can have different types of distribution of precipitation. And then it is very important, what I was showing here, to understand when this precipitation will be there and what will be the climate then. It will be very short and very wet. It will be very hot. Will the water have time to infiltrate? Will most of it will be lost to evaporation? Because you can have if you speak, for instance, on a yearly basis, you can have an increase by about, I don't know, maybe 20, 40, 50% in the amount of precipitation. But if this is not happening at the right time, in quotes, for infiltration, then you can have the climate models will basically tell you that you will have an increase by 30% of precipitation, but the recharge will increase by only 5%. Or you can have a decrease in precipitation by about, let's say, 20%. But if the decrease is happening exactly when the recharge is happening, you can have a decrease in the recharge by about 40%. So you can have these processes in the karst can very much amplify the effects of climate change. So you can have, for a small change in the precipitation amount, overall precipitation amount, depending on when it's being distributed, you can have a larger change in the amount of recharge. And yeah, this I think I can it just illustrates what I was saying now. And yes, so this is just another illustration saying that here we have the input both from precipitation, diffuse, and sinks, and it is being karst. It is very important to very precisely quantify and try to disentangle between the two. How much of the spring water is coming from precipitation, and how much is coming direct diffuse infiltration from precipitation, and how much is coming from the sinks. And this is not just to come back to the previous image to show. So we have this is the water here. This is what we get through the sinks. So here is water, river entering through a ponor, and there is water coming through diffuse infiltration. And this one can exceed by far if we are to trust these values here, the amount that is coming through the river. So we can have very low amounts here and very large amounts here through diffusing filtration. Okay, and then in order to understand this, I'm moving now into this second image of the delta 13C, so the carbon isotopes in the dissolved inorganic carbon. Here we don't see the water, we just see what is being left behind. We see the carbonate deposited. And if we look at the carbon isotope in the dissolved inorganic carbon, this can tell us a huge amount of, this can then give us a huge amount of information on the processes inside the karst. So this is data that has been collected in the US, in Arkansas, and you can see here the values of the rain. So the rain is here. Here is the soil water, and you can see the values of both cave stream in orange, the spring are between the two, and you can see this clear distinction between the delta 13C of the springs during storms and that of the springs during low flow. So you can see this, the values during low flow are much larger, indicating that the longer storage of the water underground results in dissolution of the limestone and hence these higher values of the DIC compared with the water during the same springs during storms, when you have a fast flow through the rock, and basically there is no time for water to equilibrate and to lead to dissolute. And if we look into more detail, it's not shown here, but a similar kind of information collected in karst waters, we can get ideas of the transfer times during both storms and normal flow, dry flow. So this would be something that in combination with oxygen and hydrogen values in the water could give us more information on the inputs, whether the inputs in this area are coming mostly through sinks like here, or is it extreme events like this tropical storm Grace that are recharging the aquifers in the area. And of course, this is not, it's because of the huge heterogeneity of the karst in the area. This cannot be will not be the same for all springs. Some of them will be mostly fed by ponors, and the others by a combination of ponors and diffuse recharge. And this combination will be very, very variable depending on the local characteristics of the karst. So it is very important to map these areas of potential in flow, and also use this type of events to pinpoint where exactly this water is coming, which spring is feeding, and then by using further stable isotopes or tracing, it can be established how much water is coming from one source and how much water is coming from the other source. So yeah, this will be my two final slides. That would be the final, and this would be with the discussion. So the yesterday talk was mostly focusing on this part, the connection between isotopes in precipitation and surface. Today I was trying to show how this changes in the atmospheric component of this three component system are being transferred to the surface and further downstream. And I'm arguing that in order to understand exactly how much water and where is the water coming from, we need to better understand what is happening inside the karst. This is almost like a black box, and then we have to complement the data that we get from oxygen and hydrogen isotopes with data of carbon isotopes and chemistry and dye tracing. So I think I will leave this here. I'm finished actually. I mean, I'm finished with what I wanted to say on my own, and I'd be happy to discuss further with based on your questions and comments. Thank you.
Thank you very much, Aurel. That was very interesting indeed. And there are questions and comments coming in. Again, like last week, like on Monday, if you have a question, please raise your hand or place it in the chat. The presentation will be sent to participants. Well, Jervian, again, I wrote the question. I'll invite her to speak at this time with your question.
Okay, good morning again. Thank you for a very great presentation, Mr. Persu. I hope I'm pronouncing that right. Okay, so my question, okay, my question would be, so you mentioned about the springs, right? And
Yep.
the fact that the result was a little bit unexpected. So I was wondering where the sample point was for the samples collected from the springs, because, well, I'm not really familiar with geography, but would the springs be exposed to precipitation, and would that direct precipitation have some influence on the delta O18? So of course you said that there are other diffuse sources, but I'm wondering if just the precipitation itself, would that also have some impact? That's the first question. And in terms of all right, let me ask the third question first. So I noticed that all the figures are negative, right? So you have negative. Yeah. I was wondering why that is the case. And also, so the tropical storm Grace, it basically reduced the delta O18, right? So I'm wondering if this is because of the reduced temperature. So the presence of the delta O18, or the presence of the isotope in the water vapor, is dependent on temperature changes. So is it just the fact that there were lower temperatures, and that's what is causing this reduced delta O18? Yeah, those are my questions.
Yeah. So for the first question, the four springs that I plotted here are these ones: the Jeep Spring, Chester Spring, Pasture River, and Quashis. I hope I'm pronouncing Quashis River Cave. I cannot say what are the conditions at these springs, but so these springs are discharging karst aquifers. So am I right, Geoffrey? I hope I'm right. Yes. Are these all four springs?
I have the map because one of the questions I wanted to provide some clarity and ask you a question. I was going to show the location as well, if I can do so. It might help you with answering the question.
So the point is here that the water that has been collected in these springs is water that is coming from the karst. So it is not these springs. So the sampling was done at the end. It was something like 2 weeks after the passage. I think, if I remember well, it was between August 25 and August 29. The collection of the spring water and the precipitation event, tropical storm Grace, passed the area in August 17 and 18.
Yeah.
So the water that was collected in the springs is karst water that was infiltrated through different mechanisms. So, and it is spent something like 10 days underground. And you can see that before there was no change in it, and it was only now this change. So this change has to be linked to the input of depleted water from tropical storm Grace. Now I call it depleted because, and all these values are negative, because the delta O18 and delta 2H are measured as deviations from the so-called mean ocean water. And this by definition has a value of 0. So because of this, and because of the processes, the evaporation and condensation and so on of the water, that is, so the ocean is the ultimate source of all the water that is in the water cycle. And during evaporation from the ocean, because of the preferential evaporation of the light isotopes as opposed to the heavy isotopes, the vapor will be strongly depleted in the heavy isotopes, oxygen 18 and hydrogen 2. And because we express the values as the ratio of heavy to light isotopes, that means that the vapor will be strongly depleted, and the resulting water will be slightly enriched compared to the water, but it will very rarely go above 0. So almost all the waters that we are measuring are always depleted. So they are negative values, almost always. Now, what was happening during tropical storm Grace, I was looking at data that the delta 18 values, and I was comparing with the temperature. I wouldn't say that the temperature was controlling the delta 18 of the water, of the precipitation that was dumped on the area through tropical storm Grace. So in this case, I don't know exactly the distance and so on, but the data shows that there was a good correlation with the pressure. So I think it was the distance from the eye of the cyclone or the tropical storm that was the important for the delta 18 of the precipitation during the passage of the cyclone. So I wouldn't blame it, or I wouldn't put it as a temperature controlling.
Okay, thanks much, Jervian.
Thank you.
There's a question in the chat, but before I go there, I wanted to at least share the study location, so you can see the sites, so to speak, or at least the Jamaican people will be able to see the sites that we're talking about. So you have the 5 sinks here: Quashi River, Low River, Cave River, Bottom River, McNeese Spring. You have the sinks. No, those are the sinks, rather. You have the springs, the various springs named, and those are the stars. The wells are the red dots, and the rivers are the purple dots. So one comment that I had, Aurel, that we have done dye tracing tests on the sinks. All these sinks have been dye traced, and we know the emergence of the sinks at certain of the rivers. Like we know that these 3 sinks emerge Darnock and the Rio Bueno. And we know that the sinks at Bottom River and Blue River, we're not yet. Bottom River and Blue River, we know that they come out at Laughlon's Great River and Roaring River, Dunn's River partly, and Pear Tree Bottom. In the dye tracing test, we did not see any dye come out at any of the springs that we've monitored thus far. So the springs that are here, we didn't see them come out, but we saw them come out at the rivers. It could be a delayed thing, like you said. But I was wondering if you had, was there any further comment or analysis of the signature of the rivers themselves? Because like I said, we know for sure of the connectivity between the sinks and the rivers. Was that similar drop there for those rivers, or did they more reflect the groundwater, the wells, isotope setup?
I couldn't go into all the details because I didn't know, and I don't know yet the exact connections, for instance, for which spring is connected to which sink or so. So this is why I didn't go into all these details. So these are just general observations. So maybe if we can later on or something like this, have a look at all these connections between which springs discharge which ponor, then we can look more into the details. But before that, I could not say anything about it. And yeah, I see a question by Carl. Does flow in the Vado zone play a major role in the diffuse infiltration process? And if so, how fast are these dynamics? Well, based on what I have seen, and so I can only say that there is the time. So I start with the, so I am what I start. So I'll say I start with the fact that the drop in the delta 18 in the springs is reflecting the drop in delta 18 of precipitation. So this is what so based on the data and based on what I know, these things, is what I say is that these springs are discharging the water from precipitation. Now, that means that the transfer time is less than 10 days, because we know exactly when the tropical storm Grace passed. It was August 17 and 18. We know exactly when the samples were collected. It was between 25 and 30. Again, maybe plus minus 1 day, but it was like this. So it took something like 10 days for diffuse infiltration, flow through the conduits, and outflow. And if we consider a karst system in which we have a point inflow, so we have a river that is sinking underground and is flowing as a river and going out. Now, in this case, 10 days is a lot. I mean, the transfer time for these rivers in the cars is in the range of hours, something like 6 hours, 10 hours, 12 hours, 24 hours. But this is the time scale we're talking about, hours, multiple hours, let's say 10 hours. Here we are talking about days. So that means, and because the sinks were not so much depleted, but the springs were very depleted, that means that some of the water was coming through diffuse infiltration, or it was coming through point infiltration that we don't know it. At this point, because based on the hydrology of tropical karst, so the area, the limestone is strongly karstified. So that means there should be a large number of diffuse points that all together are amounting for a huge amount of water that can get underground. And then depending on how thick the limestone is and how much of this water is flowing through fissures before getting to the river, I would still say that this transfer time of 10 days is fast in terms of karst processes. So it's a very fast transfer, because I think 10 days is a short time period for, if we consider diffuse infiltration and flow through fissures and so. But this is, again, it is important to see the karst there, to get an idea of the characteristics of the limestone, how fissured it is, how thick is the limestone sequence, and how much of this flow from the surface is happening through fissures and how much is happening through conduits, like caves.
Okay.
Question by Oliver: do we have the discharge time series for these springs, Geoffrey?
We have
Yeah.
stream flow data for some of the major rivers, the Rio Bueno, La France Great River, because we monitor them on a monthly basis as part of our general mandate. Unfortunately, we don't have the discharge for many of the springs. Those would be like point source measurements, and due to constraints on time, we don't really have the time to measure the spring discharge at all the times when we go there. We'll try to see, maybe this year for the upcoming recording period, we'll see if we can try to do at least one set of monitoring of discharge during those visits. The Gyp Spring, that's right in the interior as well, and that's a very crucial spring to monitor. So we'll try to see if we can incorporate that at least a few times in the upcoming measurements, if time would allow.
Gyp Spring and so to continue on Oliver's and your comments, so Gyp Spring and Pasture Spring showed this this very marked drop in the delta 018 of the waters. So maybe there, if there is discharge data available, there, the hydrograph should show this. So it would be very interesting if available to compare the hydrographs of these springs with the delta and also with the chemistry. I didn't look into the chemistry because, again, I wanted to speak about things that I'm sure, so I didn't want to send this into uncharted territory where I cannot be very, 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 very sure on what I'm saying.
Okay. All right, ladies before gentlemen. So I'll ask Debian to go first and then Oliver afterwards.
Oh, no, that's not right. I think Oliver was up before mine. Hello, everyone. Thank you for that talk, Orla. It was a really very interesting, especially for me. I've been doing work in the Discovery Bay area, which is, I mean, if Jeffrey would bring up the map, I'm not sure if you're familiar with Discovery Bay, but it's in this, right, it's in this watershed. I'm doing a lot of work, or have been for many years, on submarine groundwater discharge. So it's interesting. I mean, I had like a bright bulb that shined in my head as soon as you mentioned about that 2 to 3 months possibly delay in the rainfall.
For the wells.
Yeah, for the wells, right, for the wells. Because what I've noticed, and I'm still yet to confirm, but when I was doing my SGD work off in Discovery Bay, when the rain fell inland, I would see an increase in groundwater discharge offshore about 2 months later. So that's curious. So that, yeah, exactly. That really was curious to me. And then of course, seeing that, what you're seeing, I can't wait to see all of the work come together. I'm very excited. Sorry, I'm a nerd, guys, for those of you who don't know who I am. But the other thing I was wondering, are you familiar? I don't know if Jeffrey, if you're familiar with all that work that was done by Larson. It is a thesis that was produced, I think it was in the 80s by a researcher from overseas. I'm not sure if you're familiar with that thesis, Oral, because she did a lot of work, you know, on the whole, you know, infiltration through that, just the Discovery Bay area, of course, of, well, near shore, near to the coast, and otherwise, you know, further in as well, where she looked at a lot of the characteristics there of the aquifer. So, you know, recharge rates, permeability, porosity, all of that was in this thesis. So I think it would be very helpful, which
it would be.
I have some of the pages. I don't have all of the pages because I've had it for many years, and I had photocopied, you know, certain pages from many years ago. That would help because there's, I mean, it showed some very high. I'll see if I can find it and send it to you.
I would be very grateful. Yeah, that would be fantastic. I mean, yeah.
And then the work, of course, by Fincham in '97, that was that book on caves, because they do have some results for flow rates in there, in the springs, in the caves at different points in this particular basin. So I think I won't even get into the values, but I think, I mean, that would be a good two particular good papers to look at. To hear more.
Yeah, well, thanks for that, Debbie. Debbie, and we do have the Fincham book, Jamaica Underground. The Larson one, I don't think I'd heard about that before, but you can send it to us, and we'll be sure to look it up because that sounds very interesting. Also, Aurel, the response.
Yes.
Any further response? Okay.
No, I think Oliver has.
All right,
Oliver,
your time.
Yes, thank you. I have a bit of remarks and a bit of questions. So I think one important thing is that, and I understand these samples are still underway, that we observe the continuation of this time series and how it may recover, let's say, go back to normal or to previous values. I think that's definitely interesting, and how much time it will take, right? And also we need to complete these time series on precipitation to also better understand how much extreme the Grace storm was as compared to other rain events, because we have not yet completed a full year, let's say. And of course, after 2-3 years, we will know much more if the Grace is really such a exceptional event, or if such values may occur more often. Then as a remark also, I want to say that when we are talking about reaction of springs to a certain rain event, of course, we have to distinguish between the hydraulic reaction, that means the flow rate, and the transport of water, which is not the same. Often the hydraulic reaction is faster than actually the water that is transported. And then for me, the big question is also in this infiltration mechanism. What water do we see actually in the springs? Like if we consider a normal infiltration, let's say non-castic, but a more diffusive infiltration, we have always this old water question. That means we are infiltrating new water, but the water that arrives at the groundwater is not necessarily the one that has rained, because there is a certain chain reaction, let's say, in the underground, and you push out old water by infiltrating young water, which is of course dependent how much let's say real castic reactions we have and how much diffusive reactions through the soil we still have. And my question to Geoffrey would be, can you give a bit of a description of these springs that we looked at here now? I mean, how big are they? How should I imagine it? Is this water coming from the underground, upwelling? Is it water coming out of the rock? Just to give us a bit of an imagination about this.
Okay, the springs on the whole are upwellings of what appears to be groundwater, relatively minor upwellings coming up. The major upwellings will be the rivers, like at Darnock Head, it's a large upwelling of a major river in Jamaica. It's about like tens of CFS or greater for that flow. The next time we have a webinar, we can show the pictures, because we do have pictures of the different sites that can show so we can see what you're looking like. But most of the springs that were mentioned by Oral's presentation are all relatively minor springs. Drip Spring is a very small spring in the interior. What's the other one again? Pastor River is similar. It's small. That's probably actually when we looking at where that sinks, we're looking at testing that for potential diatrius tests in this coming year. That might actually be flowing to a different WMU going towards Rio Pobre from what we're seeing. So it's still reflecting, but that might not be in this particular WMU when we look at the actual outflow. And
Great. So I would suggest, I've discussed with Aurel on Monday of upgrading his Monday presentations with some additional data, and I would suggest the same for this presentation also. As we have the presentation as a document, it's very nice to keep a bit of information. And one suggestion, maybe Geoffrey, you can contribute for Aurel one picture of each spring, and we can put it in an additional slide. I think that would be very helpful to get a picture. And Aurel, when do you think that the new data will be ready?
2 to 3 weeks.
2-3 weeks. Okay.
Yes, we are. So I have these 2 fellows, Marine and they have their own samples.
They're doing it now.
Yeah, they got something like 100 samples. So this will set me up back by about I don't know, a week and a half. So.
Yeah. I hope the auto sampler should have arrived, right? Not yet.
Yes, it's there. The problem is with the installing the gas, because it has to be discussed with the university, and even if it is nitrogen. Yeah.
Anyhow, I would be very grateful if we could use this presentation document, and as I said, add a posteriori 2, 3, 4 slides. Also, for example, with the data that are coming in now very soon. And we can maybe have a small group meeting about this. I think this presentation could be a very good document to enhance it a bit for the next week. So we have this data together in a compressed form. Okay.
All right. Thank
you.
Thanks so much, Oliver. A question had been asked earlier regarding the sharing of the presentations. That would be an after dialogue with IAEA and Aurel to see what would be the protocol if the presentations can be shared on a wider basis. I don't want to say yes or no right now, but I do want to acknowledge that the question was asked, and I will be following up with both parties for same. I have 2 questions for Aurel before we wrap up, if there are no further questions. With the lag response, I guess, will be examined soon. But you mentioned the dissolved inorganic carbon. The fact that we have backup copies or backup samples of everything that's been sampled thus far, could those samples be analyzed for DIC?
I don't think so, because you should have either precipitate the carbon if the samples are just as they are. No, you either should. In order to analyze the carbon isotopes in the DIC, you have to either acidify the water just to make sure that the carbon stay dissolved, or you want to precipitate it as, I don't know, some sulfate. But I don't think this happened, so I would say no. So if the samples were not acidified, or if the dissolved inorganic carbon was not precipitated, then no.
Okay, I see Oliver has a response also.
So later, this should be discussed.
Yeah,
Oliver,
I just wanted to add here. Yeah, I think with the given samples, it's not feasible to do this. We have to also distinguish, of course. If you want to look at the delta 13C or the delta 14C, we can consider this, but this requires dedicated sampling protocols. Yeah. So I think what we need to do next is to send out some of the tritium samples We have to select them because this is much more expensive than stable isotopes. So we cannot do all of them, but we can, based on the stable isotopes results, now select a subset of tritium samples and try to send them out. And then we should try to envision, let's say, dedicated sampling campaigns, maybe for some other isotopes. But we need to plan this because then the sampling procedures are different. The analysis will be more expensive. I'm thinking also about tritium helium dating, maybe, but yeah, that requires maybe an expert mission. But we should now, as we have some data together, we can look at this maybe after Aurel has finalized the last set of stable isotopes that he already has. And then we can, based on this, make a plan where we want to add additional samples.
Okay, that sounds good. Sounds good. All right. If there are no further questions, I would like to thank us all for attending. I would like to acknowledge publicly my team, who are the ones going out and collecting the data religiously every month. Mr. Maurice Wallace, Mr. Desmond Wellington, Ms. Nia Ramsagoon, Mr. Orlando Thomas, and Ms. Natalie Hutchins. I also want to acknowledge Alexia Gray, who has also assisted in collecting, and Ms. Trichery Rodriguez, or GIS person who helps with the maps. Thank you all for being here. We acknowledge, thank you, Aurel, Christos, and Oliver. Thank you, Debbie, and also for that interesting information that helps to quantify the project. We'll definitely be linking you again to hear more on that. And we look forward to more success. We're continuing collecting the data. We're collecting the next set of data, not next week, Monday, but from the end of March 28 to 31, we'll be collecting the data again, and ongoing. So thank you all, and see you when we come back to the next presentation.
Thank you.
Thank
Bye.
you. Bye-bye.